I would like to extend a cheerful welcome to all of you in behalf of the organizers. We are elated by your presence at the CV Week event organized by the AI Club of VIT Bhopal. Finally, the wait is over, and we are here with another incredible event on computer vision. We aim at providing constructive and applicable knowledge of computer vision in the upcoming sessions of this astounding event.
Before we take off with the session, I would like to thank the Division Head of AI Division, Dr. Soundaranjan Sir, for his guidance and support in organizing the event, and would also like to invite him to enlighten us with a few words of encouragement.
So, good evening to one and all present here and participants and organizers for this event. So, this is one kind of event we are organizing for AI division. It is like technical week, computer vision. You know that it's a very important subject for today. And we are talking about manufacturing automation and also image processing. Everything we are applying for computer vision techniques, and most of the top leading MNC companies are doing for computer vision technique, and AR, VR, gaming industry also they are applying for CV techniques. So that is why we decided to start here in AI Club through. We are starting complete week, 2 weeks actually, for number of lectures. Train the trainers model. Through the students, we can train the other people. So the people will be enlightened for this particular computer vision concepts, how to do a simple project at a scratch in OpenCV. So this all happened by the coordinators of this particular AI club and volunteers also. So I hope everybody will enjoy the session for next consecutive sections for this week and next week also. I thank coordinators and AI club members for organizing such an event for the technical event for the VIT Bhopal University. So once again, I thank you all. So you enjoy the whole the session. So definitely. So thank you.
Thank you, sir, for your pleasing words. I'm sure your thoughts have motivated the students to high spirits. Bracing our vision of teaching millions and making them ready for the future, let's begin the startling session. This session will be conducted by Jackson Jacob and Gusimar Singh. Over to you, Jackson.
Thank you so much, Sneha. Evening, people. I'll be one of the speakers this evening. Just give me a minute so that I could present my screen and we could get started. Sneha, Nilaba, can you guys see my screen?
Yes.
Yes.
Okay. Hello, people. Welcome to the first session of CV Week. As you can see, today's topic is Introduction to Computer Vision. Our main aim is to nudge you people just so much that you can explore this field on your own after these sessions. So without further ado, let's get started. Before 2000s, computers were used to do very generic tasks like making documents, performing calculations, etc. Now, computers can effectively see and hear things. And all of this is possible because of computer vision. As most of us know, this is the future. There are so many tasks that can be automated by using computer vision. For an example, most of you must have seen a movie called Fast and Furious Tokyo Drift. In that, there's a particular scene in which a car moves very fast and the cops are trying to measure its speed by using a speed gun. This movie is very old. This movie came in early 2000s. But nowadays, we have security cameras in which a sensor is embedded into them and they could detect the speed as well as we could get the number plate of that car. You can see there's a considerable change in both the applications and human effort is reduced. Now, before diving into the working of computer vision, let's first understand what computer vision is. So computer vision is a field of study focused on the problem of helping computers to see. It seeks to develop techniques to help computers see and understand the content of images such as photographs and videos. So in computer vision, we come up with various techniques to help computers see and understand our image. For example, just imagine where there's a program in which you could input an image in your computer and your computer will tell you what it is, how many people are there in that photo, how many objects are there, etc. There are a lot of applications of computer vision. Computer vision involves transforming the visual images into descriptions of the world that make sense to thought processes and can elicit appropriate action. What this means is that in computer vision, we convert images into things that we understand and we could deduce information from. For example, arrays. In computer vision, we convert images into 2D or 3D arrays. And you might be wondering, what information could we deduce from an array? Well, to give you a small example, if we can detect any sharp changes in the elements of the array, we could say that an edge has been detected. More of this in the coming sessions. So computer vision is a multidisciplinary field, which basically means that it combines several fields of study. As you can see in the diagram, computer vision is a subfield of artificial intelligence and machine learning. We could also say that computer vision is a subfield of deep learning, as if we are going to create models which could classify or predict by using images, we need to incorporate deep learning with computer vision. And the main goal of computer vision is to use the observed image data to infer something about the world. This is exactly what I said in my last slide. Now, we know what computer vision is, but how to perform operations in computer vision? For that, we have OpenCV. Now, OpenCV is an open source library that includes hundreds of computer vision algorithms. It is one of the most popular computer vision libraries. OpenCV has literally everything. You could detect edges, you could detect faces, you could detect people, you can do anything by using OpenCV. And if you want to be a pioneer in the field of computer vision or just thrive in the field of computer vision, you need to have a thorough understanding of OpenCV. Over to you, Bhaiya.
So, hello everyone. All right. So the objective for today is to introduce everyone to the fundamental operations that we can perform easily using OpenCV. They might seem rudimentary to the eyes of a novice, yet any veteran of this field will inform you of the significance of these operations. We basically use them every day. They are a very small piece of the puzzle, but without them, the puzzle is basically incomplete, right? So the first and the most basic thing is reading an image. So how do we visualize the world, right? We visualize the world based on the contrast, the brightness, and based on the amalgamation of the colors R, G, and B, because these three colors basically form all the colors that we see on the spectrum, right? And that is how even computers visualize the images, right? So each pixel or each frame of an image is actually decided, the value for the frame is actually decided by the brightness of that frame, right? And that brightness is reflected by a number, and that's how we read the part of the image. For an for a model or for our computer, it's just an array of numbers, right? And the number being the brightness of that part of the picture. Okay. Once we are done with that, we extract the RGB values of the pixel. So we extract the intensity of red, the intensity of green, and intensity of blue, because these three colors again form the entire colors that we have on the spectrum. So if we have the exact values of these three colors individually, we can identify the color that we need, right? And once we do that, we extract the region of interest. So usually an image is not focused on our focal point, right? It has a lot of extra noise. It has a lot of extra things going in the background. And obviously we do not want our model, our prediction to be deviated due to that noise. So it is always important to maybe crop the image to just have the region of interest so that other segments of the image, which are basically noise to us, do not actually cause changes to our model. So that is extracting the region of interest. And then we can form several operations. We can resize the image. So the question would be, why do we need to resize the image? The answer is very simple. So generally, when we actually provide an image to a model or to a computer, our computer understands the image just on the basis of that exact image, right? So the height and width of that image is basically the focal point for understanding. So if then we move on to provide another image of different dimensions, our computer will basically be puzzled because the array that it had previously is different from the array that it has currently, right? So learning process is almost impossible. It will throw an error and it won't understand. So it is important to resize all the images to a one set definition size so that our model can actually learn from it. So that is why resizing is also very important. And then we can, rotate our image. We can add Gaussian blur to it as we learned today. And we can do a variety of operations. We can flip it, we can crop it. And the reasoning for that is that sometimes a model, like sometimes the data set that we have is so small that it is very difficult to be able to cause predictions to it, right? So causing these simple changes like rotating all the images and adding them to the data set or cropping them or maybe even flipping them, right? It can actually increase the size of the data set because in the eyes of the computer it's just an array of numbers. So if we just flip the image, it's basically a new image to the computer and it can actually learn from it, right? Generally we always take the best thing as the example, right? So we will show the image and show the laptop an image of a lion, right? We'll show it the best image of the lion, but we need to realize that a cropped image of a lion or a flipped image of a lion, or if a lion is at the corner of an image, is still a lion. So if we want it to detect a lion, we need to give it every aspect that we can have in real life that we will identify as lions, right? So these are rudimentary operations we can perform to help improve the accuracy of our predictions, right? And that is why these are very simple yet important operations. Then we can draw a rectangle. Generally, drawing on images is done to point out the region of interest. So this was a region of interest in the image, right? So we can draw a rectangle, circle, and so on and so forth. And then we can display using text. So generally, people display the accuracy or the result on an image using text. And that's it. Our output is ready. So let's move on to the next slide. Right. So now types of images. So like in real life, we have binary, grayscale, and colored images. And some of you might be feeling that, okay, it would be easier to deal with a binary image than a colored image, but that's not the case. The only difference that we go on is the amount of information, right? So a binary image has very little amount of information when compared to a colored image. That's the only difference here, right? We just are increasing the amount of information in an image or the dimension of our array. So let's go in. So let's go further in detail about it, starting with binary image. Right. Next slide. So binary image, let's say we have a novice artist here, right? A novice artist won't try to draw shades. He won't try to, understand the representation of colors in an image. What he will do is just draw an outline of an image, right? Or just draw the darker parts of the image and leave the rest of the page blank, right? That's what a novice drawer does. Because to a novice artist, the only objective here is to make sure that the picture looks presentable. And that's what a binary image is, right? We are just coloring some segments of the image and we are leaving the rest of the image blank. And the segments of the image that we are actually coloring, as black color can be represented as zero, right? Because they are basically absence of light, which is zero. And the rest of this image can be represented as white, and white can be represented as one. So so a pixel will either be zero or it will be one, right? So it's basically a binary representation of image. Now, sometimes if we take an actual image, it might be grayscale, it might have a lot of shades. But let's say that our idea is to not worry about the shades of an image, then we can just suggest a threshold value, right? And every pixel above that threshold value can just be white, and every pixel that is below that threshold value can just be black, right? So let's say we have an image of varying intensity between 0 and 1. We can suggest that, okay, any pixel with having brightness greater than 0.5 is 1, and any pixel having brightness less than 0.5 is 0. And that's what a binary image is. It is a representation of image in the forms of zeros and ones, right? So it's basically a one-dimensional array, right? Every pixel is having 0 and 1. We can even show it as two-dimensional arrays, right? If we make the height of an array a dimension and the width other dimension, we can represent every pixel as 0 comma 0, and then the intensity of it would be either 0 or 1. So essentially, a binary image is just a two-dimensional array. Now let's move on to the next one, that is grayscale images. So grayscale images is just an extension to binary images now, right? Now we have moved on from being a novice to being a little bit more skilled. So we are worrying about the shades of the images. So generally, we have 256 different levels of gray, and that is our options. So we have values from ranging from 0 to 255. 0 obviously being black and 255 being 1. That is white, right? So now we are worrying about these. So instead of having either 0 or 1 in an image, right, either it's being white or black, we are deciding to add the intensities of every pixel. So whatever the intensity of that pixel is between 0 and 255, the value is stored as it is, right? So we still have a two-dimensional array, right? It's basically the same, but now we have a larger range of values, and that could cause problems to us, and we'll learn later how to deal with that. So because obviously when we want our model to learn, we wanted our values to be of very minimum range, right? So that's the only difference between a grayscale image, right? It has varying level of intensities throughout the image instead of just having a binary value. But it's still in two dimensions. It's still, length and breadth. And we have, instead of having 0 or 1, we just have the intensity of each pixel. Now let's move on to colored images. So for colored images, as we discussed earlier, we have the RGB values. So red, green, and blue basically form every value of color that we have, right? And the amalgamation of them can form any color on the spectrum. So if we want to decide the color that the pixel have, or we want to inform of the color to the model, what we can do is just store them separately in the RGB format, right? Or some even store it in the BGR format. It's a choice. So when we store it, we'll have the values of the amount of red, the amount of green, and amount of blue on every pixel. So what we have done essentially is added another array having three values to our original array, right? That's it. So instead of having a two-dimensional array, now we have a three-dimensional one, right? But essentially, the idea is the same. It's still an array of numbers, and the array of numbers is informing us of the pictures. Now, just that instead of having 0 or 1 for a pixel, or having an intensity of for a pixel, we have a array for a pixel. And the array is informing us of the red, green, and blue values that we have for that exact pixel, right? And that is how we understand the color of a pixel. Let's move on to the next segment of our presentation. That would be 2D and 3D images, and I would ask Jackson to take over from there.
Thank you, Bhaiya. So 2D images. As the name suggests, these stands for two-dimensional images. The two dimensions being length and breadth. These type of images can be drawn on a plain sheet of paper without missing any of its parts. So basically, to give you a real life example, during our exams, the sheet on which we write, that's an example of a 2D image. And our eyes can easily perceive a 2D image as well as the computer. This is the reason why during the entirety of this week, we will be working with 2D images only. Over to you, Bhaiya.
So talking about 3D images, I like we discussed earlier, moving from binary images to colored images is just an expansion of information. The same is for 3D images, right? A 3D image is basically an amalgamation of different 2D images, right? Everything we visualize is 3D, right? But the only addition to the information is just another dimension. Instead of having width and breadth, we also have the height, right? That's the only addition here. So if we see a cube is basically 6 squares, right? So if we just store all the 6 squares, the information for it in an matrix or in an array, we have our 3D image, right? That's it. So basically what we are doing here is taking different segments of a 2D image and storing them together in a, in a complete set, as a complete set, to understand what a 3D image is. So what we have done essentially, instead of having a 3D array now or a three-dimensional array, we have gone on to having a four-dimensional array. That's it. Now we just have a set of array for every 2D image, right? And for every 2D image, we have the length and width. And for every pixel on that length and width, we again have the R, G, and B values. So at the end of the day, an image, or when we say that the complexity of the image is increasing, it's nothing but the information that is increasing. And obviously that managing that information is essential to learning CV, right? Or image processing, right? So I think that's enough theory for today. Everybody is all obviously interested in coding here, and I too find coding more interesting. So I would ask Jackson to take over from here, and let's start with the code along section of today.
Yes. Let me just open up my Jupyter notebook. Um, can anyone of you confirm if my screen is visible?
Yes, Jackson. Yes,
Okay. So, guys, let me ask you something. What was the first thing you did when you learned a programming language? I know the most obvious answer will be print hello world. This is not the case here. We will do the most basic thing that one does while learning CV, which is taking an image as an input. So for this, we first need to import our libraries. So as I said earlier, that for at least thriving in the field of computer vision, you need to be very good with OpenCV. Import the CV2 library. We will also import matplotlib, because in Jupyter Notebook, there's a certain issue that you can't open your images by using CV2. At least that's the case in my device. So that's why I will use matplotlib to input to show my image. Now, for reading an image, what I'll do is I will create a variable and I will use the imRead function, which will basically take only one um, parameter, which would be the path of our image, right? Let me just copy the path. This is the path of my image. If you have any image in your computer of .png format or .jpeg format, you can use that. But make sure that the path is absolutely correct. Most of the errors come because the path might not be correct, right? So here, and I will use matplotlib to just show the image. Okay, is this what I wanted? Actually, no, because I was hoping my image would be normal, but it came here with a blue tint, which I don't require. This basically happened because for some reason in my notebook, it converts a normal image into an BGR image, which is not what I want. It might be the case in some of your laptops too, but if this happens, you have nothing to be worried about, because what you can do is simply convert this image from BGR to RGB. Let me just show you. Fine. I'll create a variable which is img RGB, and I will use the CVT color function, which will basically take two parameters. The first one being the original image, the second one being the conversion, right? So here, let me just type. I'll just tap to autocomplete, and here you can see there are a lot of functions. So since I want to convert my image from BGR to RGB, what I'll do is I'll put BGR to RGB. Simple, right? We do this, and then I'll show my image. I'll use tap autocomplete, and here it is. Here is the original image that I was intending to use here. And this image is of Lena. Most of you who have started a journey in computer vision prior to this must have known this image because it is sort of the standard image when it comes to computer vision. Okay, so there's that. So now we know how to take an image as an input. Now, this pandemic has been host to some of the most used applications over the internet. For example, if I had to take a name, Omegle, right? It's an application which uses your webcam or a live feed. So how do we do that? How do we use OpenCV to start a webcam and further to do detections like shape detection or face detection, etc. So in this part, we will cover the part to start a webcam. So for that, I'll create a variable which will be cap, and I will use the video capture function. And it takes one parameter, and let me explain you what the parameter is. Now, if you're someone like me, you must not have an externally connected camera. I have a camera which I got from my laptop pre-installed, which is up top. So most of you must have that. But if you have an externally connected camera, then what this function does is that it gives your cameras an index. So for default, if you have a camera installed in a laptop, its index would be 0. Hence, I will put 0 here. But if you have an externally connected camera, you should put 1 here, right? And if you have 2, you should put 2. You can experiment with those values. So here, I'll simply use this. And now I will set the dimensions of my frame, which is again subjective. You might change it according to your wishes. I'm just doing this because I'm more suitable for doing this, and it will return simply a boolean value, which is true. Now, webcam, it is not a static thing, right? It is continuous. The frames are continuous. It is not like we just start it and we leave it. We need to have a loop so that it can process multiple frames. So for that reason, we will use a while loop, which will basically say if it is true, then we would read from our camera, right? So here I would just use my cap variable and read. Now, this read function gives out two outputs. The first one, which is vid, it will be the output image, which will be the live stream, and success is simply a boolean value, which can be true or false. We won't use this here, success much, and yeah, when we will run this code, you might see that our image, our live stream is there, but it is inverted. So to make it normal, we'll use the flip function from CV2, in which the parameters would be simply the video and one being the axis. That one means we'll change it from the x-axis, so it will just flip itself. And now we will use CV2 and just show the image, show the stream. It is as simple as that, guys. Now, how to stop the image, right? So for that, here's a simple line of code, which is wait key. And also we need a special function which would tell our computer that if we press a certain button, then the stream should stop, right? So here I just put this, Now, what this means? This means that if I press the button Q on my laptop, then it should break out of the loop and hence the streaming would stop, right? I hope that makes sense. Now, after that, we will simply release. Again, I've used the auto tab function, and we will destroy all windows. Right. So let's check this out. Whole screen. Just a minute, guys. I'll show you the output of this. Okay. So I hope my screen is visible. Here's the code which we wrote in the whole session, and I'll show you the output. Okay, just a minute. As you can see, here's an image of me live streaming. You can see my hand, and here you can see that the RGB values are continuously changing, which is the magic of CV2, that it dynamically changes the RGB values to wherever I point, right? And I could simply stop this by using the Q button. As you can see, it's gone. So in this part, you have learned the very basic thing, which is to read an image and to start your webcam and to stream using OpenCV. Now we will go on to the slightly more complex part, which would be operating on these images. So let me just share my screen. Are you guys following? You could just put a thumbs up in the chat if you are. Okay, fine. Is my screen visible, guys?
Yes, it is.
Yes.
Okay. So here we will perform some basic operations on images. So for that, the first things we need the libraries. I'll just quickly import CV2. There's no need of telling you guys again. You might be bored. We have used NumPy here, and NumPy, as most of the Python geeks would know, is a library which is used for array manipulations and calculations. And I would also use matplotlib for outputting the image. Then we would take the input using the same imread function. And yeah, as I said, setting the path is very, very important. After this, I'll create a kernel. Now, kernel is basically a mask, and we will tell you more about mask in the upcoming sessions. But you just need to understand for now is that these masks are very important if you want to say detect edges of your photo. So for those things, these masks are very important, right? So now I would just create a markdown saying basic operations. For those of you who are wondering, markdown is simply done by escape button, then pressing M and enter. Okay, fine. So I'll first show you the image, which is the same code which I did earlier, which will be IMG. It's again the blue tint. What do we do for this? Yes, we convert our image from BGR to RGB. I would not write it because it will get a bit boring. And I will show you the image. Yes, this is what we want. Now, as Korsiman Bhaiya said, grayscale image is something that we need to work on if we want to do operations on our images. So let's try to do that. So here I would simply, first of all, convert my RGB image into grayscale image. which would take the parameters, the first one being the image itself, the second one being the transformation, right? So we are converting it from BGR to gray. Yep, there it is. Okay, let me just show you guys. Okay, so it is not really gray. I know you guys might be like, okay, but we converted an image into a normal image, so why is it giving out this weird bluish yellowish tint? Again, this is a problem which you might not face, but some of them would face because it's basically a thing which your Jupyter notebook does. So for this, what we would do is simply um, take the grayscale image which we created, and we will change its CMAP. Now CMAP is basically in Matplotlib, you can change the color of an image, right? So here we would change its CMAP from normal to gray. And as Bhaiya said that there are two values, there are the scales of grayscale images, which is basically from 0 to 255, right? So we would set our values from 0 to 255. And there it is, the grayscale image which we wanted. Now, you all have smartphones, right? And in that, one of the most talked about feature is in the camera, which is the bokeh mode or the focus mode, in which it focuses on one part of an image and it blurs out the rest. How do we do that, right? We simply will use a function which is called Gaussian blur. Now, Gaussian blur, to give you a quick idea, is a function which is based on mathematics, based on a Gaussian distribution. I won't go into much details of that. You would get that in the upcoming sessions when we talk about filters and masks. So here we will use the Gaussian blur function. I'm just auto completing it, which will take three inputs. The first one being our image, the second being the size of the kernel, right? We discussed earlier about the kernel. So here's the size of the kernel. I'll be using a 7x7 mask. And then the sigma function, which is basically the intensity of the blur. Let's just see if our image is blurred or not. Okay, it is blur, but you might not be able to see it. If you run it in your laptop, then you could see there's a definite change in the image. First, our normal image was completely sharp and distinct, whilst this is sort of a blurred version of that image. So if you're wondering that how the cameras, the bokeh mode works, this is how it works, guys. And you might find blurring of image in a computer vision journey a lot, because it is one of the most important steps we need to do for refining our image. Now, we would detect the edges of our image, right? This is very interesting. We would use the canny edge detector. Now, the theory of canny edge detector would be discussed in the next sessions, but to give you a small example, it basically works that there will be two thresholds, right? Threshold 1 and threshold 2, and the values in between these thresholds will be considered as edges, but the values which will be less than the minimum threshold value, those values will not be considered as edge, right? So we will use the canny function here, which will take in three parameters. The first one being our image, and the second and the third being the threshold values respectively. So here I'm just setting the threshold values as 100. And to show you what I mean, you can see here it is quite frightening, but it's fine. You can see that it has successfully detected the edges of the hair, of the hat, etc. But yeah, you might have this question that Yeah, all this is fine, but how do we refine the edges? Like if there's a certain edge that it is missing, how do we refine that? So for that, we will use the dilation function. Basically, we will dilate the edges of this image so that the edges are more clearer, right? For that, I'll create a new image. And guys, it is always preferred for you to create copies when you are doing operations, because we want to keep the sanctity of the normal image. We don't want to destroy that. If you want to do any operation, we need to create a copy of that. So for this reason, you might see I'm using variables like img canny, img dilation, etc. So here we would use the dilate function, and this will again take three parameters. The first one being the canny image, because it needs to define the edges. So we need an image with an edge. And then we'll pass our kernel, which I talked about earlier. And then the number of iterations, which I would go for one. You could always play around with that. And to show you the dilated edges, here you can see that the edges have been magnified, right? But yeah, all this is fine. But this looks a bit like it has a lot of noise in it. Like you can see the background, the edges are magnified, and it is somewhat interfering with the main image of the lady. So how do we minimize the noise, right? We will use the erode function of CV2, which will basically remove the noise from this image. What I mean is, I would create a variable, eroded, and I will use the erode function in the CV2 library, which will take in three parameters again. The first one being the dilated image, the second one being the kernel, the third one being the number of iterations. I would again go with one. And to show you what I mean by reducing the noise, here you can see a considerable change in both the images. As you can see, the darkness or the intensity of the edges has been reduced, and the background, the edges have been reduced quite a lot. Hence, we can only see the edges of the lady. So yeah, these are some of the basic operations. There are a lot of operations when it comes to images, but these are the ones which will be used mostly in the upcoming sessions. And yeah, now we will go to resizing and cropping an image. Bhaiya, you can take over.
All right, let me start with sharing my screen. Are you able to see my screen?
Yes, I am Bhaiya. Go on.
All right. Okay, so we'll start with resizing and cropping images. As we discussed earlier, it's really important to resize or crop images because our model always looks at an image of a set size, right? If we provide it with images of varying sizes, it won't be able to understand or learn from it. So it is always necessary to set a size beforehand. So the first thing we'll do is we'll import CV2, right? The most basic function here, right? So it's CV2 is basically the library we are using, and the segments of code have already been written for us so that we won't have to work hard, right? Now we'll read an image. So I'll read using cv2.imread. So we have our resources folder, I guess, here. Right? And the image I'll be using today is cat1.jpg. It's not cat11. Okay, yep, cv2 should be. Yeah. So remember. All right, so after reading the image, we'll be doing two operations today. First is resizing, and the second one is cropping. Right? Let's start with resizing here. So there's nothing more to be done by resizing. It's a very simple function, but always remember to save it in a variable or the changes won't be saved, right? So I'll just do the resize. So the first parameter here would be the source, and the second would be the new dimension, that is the height, the width. So parameters here are source, comma, edge, right? These are the two parameters that we need, for resizing the image. Now, cropping the image is even simpler, right? So anybody who has worked with Python before must know about slicing, right? Slicing is a very simple feature in Python. It means nothing but taking a subset of an array, right? And as we discussed earlier, images are nothing but an array of n dimensions having information of intensity of brightness, right? So if we go through and we slice the array, right, and we say, okay, so from the y-axis, take the numbers from 0th index to the 100th index, and for the x, take the values from 100 to the 200 index. Our image is now cropped. We have a subset of an array, and a cropped image is basically a subset of an image, right? So that's it. Yeah. And now let's see the shape, first of all, of our resized image, right? So this should be our shape of the image and the shape of the resized image. Size, shape. So yeah, so as you can see, the shape of the original image was, a random shape, and then we set it to a particular shape that is 300 in height and 200, and we can see the shape here. This 3 is nothing but the RGB values as we discussed before, right? It is just our channel. So for CV2, it's BGR, not RGB. So the parameters again here, like the value that we get are height, width, and channel, right? So we already have three values here. So now let's see the image, right? Let's just see the original image first. So we'll be using IM show. This is our original image, and the source for it is IM, and I'll be using wait key here. So wait key is nothing but it is asking us to wait until we have seen the total image, and 0 tells us just do not remove the image until we tell you to, right? So it has been only different, and this is our original image, right? Okay, so it's here, and we can see that it is basically a very small image, and this was our original image. Now let's move on to seeing our resized image. Source here is img resize. Okay, and we'll have to write the wait key. So this is that resized image. So as you can see, the images are now a bit lengthier, right? We can see that it is a bit more stretched now, right? And that's the very simple difference here. And now let's finally see the cropped image. We have our img here. Let's see, v2 dot a is capital and 0, right? So we have our img cropped, right? It's called img cropped. Once we run it, we have a cropped image. So we have only cropped a segment of the face here, and we can see that segment of the face. So these are very rudimentary operations that we might be using, in the future. So let's say we also want to have our image, a bit broader, but we do not. So we want to resize an image into a larger image, but we do not want the pixels to lose information, right? That's what happens sometimes when we try to stretch an image, right? So we just want them to be behind the black screen. So for that, we can just try to superimpose pictures using offset as well, right? So I can just import NumPy. As Jackson discussed earlier, it's a library used for higher order mathematical functions if we require ever in Python. So let me just import NumPy for it, and let me create an image using NumPy. So as we discussed that, let's say it is a larger image, so image underscore L, np dot zeros. So what np dot zeros does is basically it makes an array of the set dimensions. So for us, the set dimension is 512 by 512, and 3 is just again the channel, right? It makes an array of zeros. So an array of zeros is basically a black image, right? It's basically the same thing. So let me make the array. Okay, so we have a larger image now. Okay, the issue here is that I did not rename numpy as np. Okay, right. So once we do this, what we need to do is it's units. All right, let's see about this a bit later. I think I've made some error in writing something here. I have the thing written here already. Oh, I wrote it's not unit, it's UINT. I wrote it wrong. Apologies for that. Right. So let's move on from that. So it's UINT and it's not unit. Okay. So once we have a black image, what we need to do is we need to identify the position where we need a new image, right? So we can just use X offset, right? For the offset of X, and let's say we use the Y offset for the offset of Y. We just decide it to be 50. Right. So again, we can use the idea of slicing here, and what we can do is we can just set the larger images portion that we want, and we can set it to a smaller image, right? So what we can do here is we can say that, okay, take the segment of the larger image, right? Take the Y offset as the image. So what we need to do here is that we need to identify the shape of the smaller image, right? So we can also use the values here because we already know the values, but it is always better not to hard code values. So we can use the smaller images shape. We already know it's 159 and 318. So the value that we are using here is 318, right? But if we can just use this, it would be always better so that in the future, let's say we change the image altogether, we do not have to hard code these values again and again, right? And then we add the Y offset to it, and then we can add the X offset, and we can add the X offset here, which is basically the same as Y offset. Okay, Y X, yeah. And once we have sliced our original image, right, we have sliced our image L, and we need to set the values of that offset as a smaller image, right? That's all we need to do. So when we run that, okay, I forgot to finish the segment here. So what I did here is I added the X offset twice. Yeah, and our X underscore offset is basically image shape one dot X offset. Image underscore L is defined. That's my bad here. Yep. Okay. Making a lot of errors. Yeah. So our y offset again is shape of the zero of a smaller image, and we are just adding the y offset. And when they are taking the y shape of a smaller image, and then we are just adding the offset to it, right? So if we just see this image now, what we'll get is if we see the larger image, that our image is again resized. Right. So as you can see, instead of having a gray background, we now have added a black background to it. So now basically our image is of 512, 512, but we have not lost, the information in our original image, and we could have easily resized it into larger shape. So let me go through that once again. So basically we are taking the larger image, right, and we are trying to slice it, larger image, and we are trying to slice it. And the y, the point where we want to start slicing it from, the y position, is the basically the shape of the smaller image, shape of smaller, plus whatever our offset is that we want to be. So however far we want it to be from the edge, offset. And then the x is same, shape of smaller for x, right? And then whatever the offset for x we want to be, or however far we want it to be from x, right? And then we are just setting it to the smaller image. And this is how we can actually resize an image into a larger image, right? All right. So why would we want to do this again? Right. So this is how we see an image, right? But this is how our model sees an image. It takes the intensity of everything and it tries to aggregate it, and then it shows us the intensity. Right. So when we flip these images, when we crop these images, basically they become a new image altogether, right? So let's say we have a data set of one image, which is not right, not very true in real life, but let's assume that, right? We can easily make a data set of one image into a data set of 12 images by just manipulating the images themselves. Thereby we have a larger data set and we have realistic scenarios included, right? That is why these operations are important to do, right? Now let's move on to the next, that is drawing shapes. Right? Okay, so again, what we'll do first is we'll import numpy, right, as np, and we'll import our first library, that is cv2, and we can easily run it, right? So this time we are adding shapes, so we can again use a simple black image, and that is why I've used numpy here. So we can use np and we can fill it with zeros again. So the shape of our image is 512 comma 5512, and again we can use np dot, right, and uints uint 8, right? So let me just make sure that I'm doing let me just make sure that this was the syntax, because I tend to forget it a lot. uint, that's right, great. So once we run it, we have basically an array filled with black. If you want to shape the color, let's say if you want to recolor the image, I'm sorry, you can just use this simple operation, right? And this is how we can change the color of the image from black to blue, right? Because it's b comma g comma r, so whatever value that you will give here first, the color of the image will be that, right? Right. And now let's understand how we can draw shapes in it, right? So that's the objective here. Drawing shapes. Okay, and lines. Right. So let's analyze the syntax of drawing a line first. So we can simply use the line function in CV2, pretty simple. Then we have the source image here, right? Then we'll have to add the start point, and then we can use the endpoint. Right? That's what our line has, a start point and an endpoint. Then we can give the color and the thickness. That's all we need, right? And that should be it for a line. So let's make a diagonal line, okay? Diagonal line across. So for having a diagonal line across, we'll use the line function first. The source is the image itself, right? The start point would be 0, comma 0, the top of the image, right? And the endpoint would be the shape of the image, right? Because basically 512 comma 512 is the endpoint, which is equivalent to the shape of the image again. So instead of writing 512 comma 512, I can just write image dot shape 1 comma img dot shape 0. It, right? And the third thing again we need to add here is the color. So color again, I'll just make it blue. Why not? Yeah, blue. 0 comma 0, and then the thickness of the line. So thickness could be anything. I'll just give it a thickness of 3. And that's it. We have added a line to the image. Now we need to understand that this function just adds a line to the image, right? It is not making a new image and adding a line to it. So basically the sanctity of our original image will be lost after this, right? So it is important that when we are using it in real life scenarios, we just copy the image before or save it in another variable and have our original image as well, so that the sanctity of an image is not lost. So we can just say something like, we can just make another variable img2 and save img in it, and then do all operations on img2, so that our original image remains intact. This is something that we also do in Photoshop, right? We, whatever changes we make it to a new layer, right? So that the original image always remains intact, right? Okay, let's see, we do. Right. So it has made changes to the array, and here we can see the array itself. So it has just made a few changes, and that's the changes that we can see. Now we can just use I am show again. The source is image, and we'll just say that it's a line. And then again, we'll have to use wait key. And when we run it, we get our image. So as you can see that we have our image here, and the line is basically there, right? It's a black image with a line on it, that's it, right? There's nothing special about it. Okay, so now that we have added a diagonal line, let's try and add a rectangle, right? So rectangle. So now if you must be wondering what we need to do to add a rectangle, right? Again, we'll add the source, right? That's the first thing that we need always, the source image, right? The start point again. Now, some of you might be wondering, okay, we'll just give the 4 points that we require and that's a rectangle. But actually the 4 points are not needed, right? Because at the end of the day, if we give 2 points at a diagonal, we get a rectangle, right? If we have a line, if we have the diagonal of the rectangle and the edges of the ends of both the diagonal, we can form a rectangle with it, because a rectangle always have 90-degree lines and the opposite sides are equal. So we just need the endpoints of the rectangle. That's it. We do not need to define the whole 4 points, right? So I'll just give the endpoint of the diagonal to be 250 and maybe 350. And then we can give in the color, any color you want. Um, and finally, again, the thickness. So yeah, that's it. So let's try to write it. 0, comma 0, 250. I'll just give it the color. I'll give the same color. And instead of giving a rectangle with thickness, we can also use cv2.fill. So what cv2.fill does, it instead of giving it a thickness, it actually just fills the triangle altogether, right? So we can use cv2.fill, but I'll just be using 4 here. It's a choice again. All right. So obviously we'll have to give the rectangle function. We have to use the rectangle function here, and my source image here is img, right? All right. So we have made the changes. So I can just use the same thing and call it a rectangle this time. So as you will see again. Okay. So for some reason it is giving it a black color here. That's odd. Okay. Let's try to make it 255. So we do that. All right. 0 and 0 here. Yeah, so now we have a white rectangle here. I think there's some error going on in my CV2 right now. That is why instead of using RGB, it's giving me white colors. All right. Right. So now let's just try and add a circle to it. So again, we can simply use cv2.circle. We have our source image, and this time we just need to define the center of the circle, right? We have the center, and if we have the radius, we can define a circle. We can simply use the formula um, x square plus y square equals to r square to define the circle, but that is the formula being used behind the scenes. So let's define the radius of the circle as 30 and define the point as 400 comma 50 so that we can actually see the circle, right? And then again we'll define the color, so I'll just define it at 255 comma 0 comma 0. And then again we can use cv2 dot filled, or we can decide a thickness, like we decide the thickness as 6. So that's it. That's a circle, right? We have the start point, right? We have the radius here. We have the color and we have the thickness. So again, parameters are source, start, source center, radius, and the color, thickness, right? So let's run. Now we have added a circle to it. See, so we have a circle added to it, at the edge of it. That's about it. And finally, let's add text to it, right? So that's the only thing left. So for this, I'm going to make another image. So I'll just call it img2, right? Because it's getting a lot crammed in there. So let's make another image, right? And let's just add text to it. So we'll be using cv2 dot put text. You can simply use cv2 dot put text here, right? And we have the source, right? We have the text. So I'll just call it CVP, right? And then we have the start point for our text. We can just give it anything we want. Then we'll have the font. So CV2 dot. We can give any font. I'll just use the most generic font right now. Font Hershey Dupli, right? And then we'll have the scale of the image. So let's scale of the text. So I'll just define the scale as 3. Then we'll have the color. So I'll just give 150 comma 0 comma 0. And then 1, right? That's about it. 150. So basically the parameters here are the source, the text that we want, right? The start point, font, right? The scale that we need, the color, and then finally we have the thickness of the text. We just run this. Okay, I guess all right. Let me just see the font here. All right, it's called Hershey Duplex. So I guess I misspelled it again. All right. So here we have our new image. We can just see the new image. All right. Wait, let me just define this as 255. We have saved it in img2. All right. So let's try on this again. Right, so for some reason it's bugging out. I hope that you can see this on your original thing because it should work. Wait, let me try and open a different one here because it should be working. Yeah, okay, so it's working fine on the original one, but for some reason it was bugging out here, right? So the code remains the same. So I think you can see the CV weak text now, and we can also see the colors here for some reason. So yeah, so we have our source, we have a color, we have the text, we have the starting point. This is our font, this is the thickness, this is the scale, right? This is the color, and then finally we have the thickness. And once you do it all, you should see something like this, right? Because I did it on the other image there, it was a bit bugged. Yeah, and that's all for today, right? I hope that you had fun learning the rudimentary operations that were taught today. And if you have any doubts, you can ask. I think this is the best time to ask us. So just to end of the session, there is a small example. Why we will be using shapes and text in real life. So it's just a normal image of the crowd, and what we did here is we first detected the faces from here, right? And as you can see, all the faces were not detected. You can guess that the model was made by me. And as you can see, the things that I make are a bit buggy sometimes, right? And then we just crop the faces, and after cropping the faces, we just try to detect if they have a mask or not. And once we have the resultant for our final image, we just reflected it using a small rectangle and the text saying mask or no mask. So that's how we can use these rudimentary things in our models to make them more understandable, because the idea of making models, or basically using artificial intelligence or image processing or deep learning, is to not just make models and try to make predictions, but it is also to make them understandable to the human eye, right? Our models should always be easily explainable, right? It's called explainable AI. I think this is something that beginners of AI can have a deep dive on right now. Just surf explainable AI on the internet and you will get a lot of resources on it, right? And that's the end of the session for today. So this is the time, I guess, for any doubts, right? And also there will be a quiz soon, right? There will be a quiz
Bhaiya, can I
soon.
explain that?
Yeah.
The quiz thing.
Yeah.
So, guys, in the chat box, there's a text which says encapsulates all the rules that we need for the quiz. Basically, you need to sign in on a website known as Quizin, and using your VIT Bhopal email ID, and your personal email ID won't be allowed for this. And each participant can attempt the quiz only once. And in this quiz, there will be 5 questions, and you will get 20 seconds to answer that each question. And yeah, the this quiz will be very interactive and amazing. And to score more points than your uh, opponents, the participants need to select all the right options and complete the quiz as soon as possible. Right? I'll be sharing the code which we did today in the chat box, and I will also share the link of the quiz. Please use your VIT Bhopal email ID for this, otherwise your quiz won't be counted. I've shared the link. I've shared both the links here, and yeah, and these quizzes are very very important, because at the end of each session there will be 3 to 4 three winners, and yeah, in the end of the session we would give them shout outs and exciting prizes which we won't reveal now. And there will be brownie points for the people who will be attending the Kahoot session, which will be hosted on Kahoot on Friday. Yeah, there are some doubts. Masking. Uh, we will be talking about masking in the coming sessions, specifically next week, Monday. But to give you a small insight on what masking is, it basically helps us to concentrate on the part of the image that we need by using solving a matrix. There's a lot of operations there, such as convolution, etc. And all of that will be explained in next Monday session. So yeah, Shivam, please stay tuned for that and watch out for that. There's also another question. Explain the topic again. Bhaiya, if you could please explain it again,
Yeah,
just
sure.
quickly, because we don't have time.
So I hope that you have the code with you there. So the idea of offset, again, I'll try to explain it to you. The idea for offset was that basically we have a larger image there, right? So what the larger image does is it has its own width and dimensions, right? And we have to superimpose the smaller image on the larger image, right? There is no point of having right. So basically we have a larger image that is black. It is full of 0 pixels, right? And then we have a smaller image which was the image of a cat, right, if I remember correctly. So if we want to expand the image of a cat, what we can do is just put the image of the cat on the image of on the black image, right? That should be enough to have the image back. So for that, what we can do is we can simply define at what point of the larger image we want our smaller image to be. And we can simply use, I think I've done this here. Right, no, not here. Let me find it. It's drawing shapes and lines. Yeah, this was it. Right, not even this. Image resizing info. Yeah, all right. So we are back here, right? So our larger image is just an image of black pixels, right? It is a 512 by 512 image of black pixels. And a smaller image is just an image of a cat, if I remember correctly, right? And it is very small. It is by 159 by 312 pixels. So if we just want to superimpose the smaller image on the larger image, what I've done is I've taken the larger image and I've cropped the image, right? I've taken the cropped pixels for the larger image, right? Using slicing. So what we have done is we have defined this is basically the Y position from where we are starting the slicing, right? So the Y position is the shape of the smaller image, right? So the shape of the smaller image is 159, right? So we can just replace with this 159, right? So if we have 159 here, right? So the image is going to end on 159, right? So it will start right now. Our image will start from 0 and it will end on 159, right? But let's say we do not want it to start from the start of the image. We want it to start from 50 pixels later. That is why the Y offset has been added. Offset is nothing but the amount of blank area that we want to leave at the start, right? So we just say 50 and here it will be 50 plus 159. Okay, so now the image will start 50 pixels later. The same is for X, right? We take the X offset, right? We take the X shape. So the shape for the X was 318. So we just take the 318 and we said, okay, we want only 318 pixels of the larger image, right? And we want the first 50 pixels to be left out, right? That is why the X offset has been added. So we start from 50 and we end at 318 plus 50, right? So now basically we have taken the image, right? And this is how we are going 50 to 318 and we have cropped the image, right? Once we have cropped the larger image, this section, we just add a smaller image to these pixels, right? So if we add anything to a black pixel, what we'll get? We'll get the image itself, right? Because the brightness 0 is added basically to the image, right? So we'll get the image itself. So now this cropped portion of this image, larger image or the black pixels is basically been set to the smaller image, right? In simpler terms, let's say we have an array 1, 2, 3, right? And what we do here is we take this array and we say, okay, we call it ARR, let's say, and we say, okay, ARR0 is set to 3. So now what we have done here basically is ARR0 is set to 3, or let's say we say AR0 to 1 is set to 3, right? So now our ARR becomes 3, 3, and 3. That is what we are doing here. We are taking a larger array. We took the subset of the array and we are setting it to a smaller image, right? And the offset here is basically the number of pixels that we need to leave blank before setting our image, right? So this 50 offsets define that, okay, our pixel range will start from 50 and it will end at 50 plus the size of the smaller image. Does that make sense now?
Yes, I think his doubt has been cleared. So, guys, please go and attend the quiz as it is very fun. I've attended myself, it is very fun. And I would like all of you guys to just turn on your camera so that you could commemorate this event. Okay. Yeah, smile, people. Okay, thank you guys. Thank you guys so much for attending and being a part of this wonderful session. And all of our sessions would be hands-on based so that you guys could just feel how easy it is to get started with computer vision. Thank you, people. Please stay tuned and please attend the quiz. Thank you, guys.
Firstly, a massive thank you to you, Jacob and Gussamer, who enlightened the students and graced us with their presence in their busy routines. We would like to thank all the faculty members who entrusted their belief and blessed us with this opportunity to conduct this event.
This event wouldn't have been possible without the sheer support of our student coordinators, leads, and the team. Once again, I would like to thank everyone for attending this event and for being such a great audience. We look forward to seeing you at the club in the future. Thank you, on. Thank you all. You can connect with us, and we'd love to hear your feedback over our social handles. Thank you once again.